Previously, we have discussed in very detail the problem of motion of particles in central force field. Sorry. Actually, while discussing the motion of a particle in central force field, we have discussed so many important facts. We have seen that motion in a central force field always takes place in a plane, and we have discussed the trajectory of a particle moving in a central force field. As you know that the central force field may be either attractive or repulsive. For example, you know the gravitational field force is a central force and it is attractive always. While when you see the another example, the electrostatic force that may be attractive or repulsive both. When the when you consider the Coulombian force between two charged particles of same charge, that is charges of same sign, then the force is repulsive. But in case of charges of opposite sign, this is attractive. Okay. And you know, you have discussed the bonded and the unbounded motion in central force field. Actually, when the motion takes place in an attractive central force field, then eccentricity of the path of the particle is less than 1 and the orbit is elliptical as the orbit of planets. We have discussed the Kepler's planetary laws of motion. Okay. And such a motion is called bonded motion. But if the central force is repulsive, the motion is unbounded. And in that condition, the eccentricity of the trajectory of the particle followed while moving in a central force field is greater than 1. And the path in general is a hyperbola, and you simply say that the motion is unbounded. Okay. Now actually, in this regard, a very important problem of scattering in central force field you face. And this problem of scattering is very important, and I have already discussed in my previous video the basic fundamentals of the scattering problem in a central force field. And we have discussed the important parameters in terms of which the scattering problem is discussed. And in this regard, we have seen what is differential scattering cross section, and if you know the differential scattering cross section, then how you can calculate or how you can find the total scattering cross section. Because the core problem, the basic problem of scattering is to find the differential scattering cross section and the total scattering cross section. Actually, this scattering problem is very important both in classical mechanics and in quantum mechanics. But here our concern is related to the classical mechanics where we do not follow the quantum mechanical approach, but we follow the classical approach to deal with this problem. Sorry. And when you say that we are dealing the problem of scattering in a central force field, one of the most important example regarding this is Rutherford scattering. You know, Rutherford and his student Geiger and Marsden have performed a very famous experiment, and that experiment is one of the important experiments of physics which actually provided a new path, a new way, a new light in physics. And that very important experiment is known as Rutherford alpha scattering experiment. Actually, in that experiment, a beam of energetic alpha particle was incident on a target of gold foil, and the alpha particle gets deflected or scattered. And from this very experiment, Rutherford developed his model of atom, which is actually called the nuclear model of atom. And the nucleus was discovered. This was a very famous event in physics, and after which the modern science was started. A new look into the interior of the atom was due to Rutherford. Okay, actually, uh, this problem of scattering of alpha particle by the target or the nucleus we will discuss here. So this is a very important problem, and it is equally important for the students preparing for different university examinations and also for the competitive examinations like the Union Public Service Commission, that is IS examination if your optional is physics, and also for various state level PCS. Because when you will see the previous year question, you will find that frequently questions have been asked related to this Rutherford scattering in these examinations. Okay, so watch the video seriously, and definitely you will get benefited when you will watch the video seriously. Actually, I have written each and every aspect of this problem here for your convenience, because that will be a good notes for you, and you will we will you will learn the logic, the calculation, and apart from that how we can write answer for these examinations, that you will also learn. Okay, actually the Rutherford scattering problem is a vast problem, and for simplicity and particularly for your convenience, I have divided this lecture in two parts. I can complete this lecture in only one part, but if I will complete it in one part, in one lecture, in one video, that will be somewhat uh, more elongated, more lengthy, and you will not feel ease. So for your ease, for your convenience, I have divided this lecture in two parts. Actually, in this first part of the lecture, which we will see today, I have discussed only uh, only one part of the scattering problem, and this is actually the calculation of angle of scattering, and how this angle of scattering is related to the impact parameter we will see in this first part of the video. But the most important part of this lecture will be actually the second part, where you will find the calculation of the scattering cross section. Okay, so let us now start to deal with the problem of Rutherford scattering, or you can say Rutherford alpha scattering. Okay, and here, as I have mentioned in this title, that our aim is to find the angle of scattering in this problem. Okay, actually, the Rutherford scattering theory was developed on the basis of some assumptions, or you can say that Rutherford uh, took some assumptions to develop the theory in a liquid and a simple manner. And as these are assumptions, so that not may be experimentally correct, but taking these assumptions, our calculation will be very easy. One thing I will also here mention that actually this lecture will need some results which you have learnt earlier. So if you have not watched my video on central force field, particularly the trajectory of a particle moving in a central force field obeying the inverse square law, you must watch those videos. You will find in the playlist of classical mechanics under the heading central force field, because the results which we have obtained in the earlier lecture, that will be used here directly. So definitely if you want to know about those relations, those formulas, those results, you must watch my previous videos on central force field. Okay, Now, let us see what was actually the assumptions on the basis of which Rutherford developed his scattering theory. Basically, there are three assumptions. In first assumption, it is assumed that the target and the incident particle are merely point masses. It means we do not think about the dimensions of the alpha particle and the dimensions of the nucleus. We simply treat that the incident particle, which is actually the alpha particle, and the target, which means the nucleus of the target, both are treated just like point masses. Okay. And if you have an idea of quantum mechanics, definitely you know that these are microparticles, and microparticles have wave nature. So this problem is also dealt in terms of quantum mechanics, setting Schrodinger equation and solving these. But here, our treatment will be classical. So we completely neglect the wave aspect or the quantum mechanical aspect of these two particles, that is the alpha particle and the nucleus. We never think that there is some wave or wave packet associated with these two particles. We simply take it just as classical particles which have no dimension. Okay, this was actually the first assumption. Now, in second assumption, it is assumed that the positively charged alpha particle gets collided with or gets interacted with the positively charged nucleus. And as both are positively charged, so therefore there will be a Coulombian repulsion between them, and that Coulombian repulsion or electrostatic repulsion, which is actually obeys the inverse square law, because you know that Coulombian force F is inversely proportional to r square, where r is the separation between the interacting particles. So in this scattering, it is assumed that the positively charged alpha particle gets repelled by the positively charged nucleus, and the force of repulsion is electrostatic, that is Coulombian, which obeys the inverse square law. Okay? But you know that in our target or in an atom, apart from the nucleus, there are electrons. If your target has plus Ze charge, that is the charge of the nucleus is plus Ze, where Z is the number of protons, definitely there will be a Z number of electrons too, and electron is also negatively charged particles. But in this interaction, we never think about the charge of the electron. Or in other words, you can say that we never thought that this interaction will be affected by the presence of electron. It means the presence of electron is completely neglected here. Okay? So this was actually the second assumption of this theory. Okay? Now, the third assumption says that the scattering nucleus, or you can say the target nucleus, has an infinite mass compared to the mass of the scattering particle, that is the alpha particle. It means we consider that mass of the nucleus is infinitely larger in comparison to the mass of the alpha particle. So in this interaction, nucleus will be never in motion. Nucleus will be at rest. We consider it, we assume it. Although when the mass of the nucleus will be comparable to the mass of alpha particle, both will be in motion, and then this will be a two-body problem. But this problem is dealt like a one-body problem. We consider that nucleus remains stationary during this interaction. Only the motion of the alpha particle is affected. Nucleus remains always at rest. During the whole process, nucleus is never in motion. It is always static. So these are the three basic assumptions on which Rutherford alpha scattering theory was developed. Okay, I think we have definitely clearly understand what are the assumptions on the basis of which this theory is developed. Okay. Now we will see the basic theory, in which, as I have told you earlier, that in this lecture our aim is only to calculate the angle of scattering. What is this angle of scattering? What is impact parameter? Already I have discussed in my previous video. Okay. And for calculating the angle of scattering, let us see this figure. Let us consider that this is a nucleus. Here I have shown the target nucleus at this point N. And let us consider that an alpha particle whose charge is plus 2e, you know, charge of alpha particle is plus 2e, where plus e is charge of a proton. That alpha particle is projected from a very large distance. Theoretically, you can say infinitely large distance from the point X along the direction XO. It means this XO represents the initial direction of motion of the alpha particle, which has been projected from this point X. Okay? From this point X. And when the alpha particle will be projected at the initial position, it will experience no force of repulsion due to the nucleus, because the separation of the alpha particle from the nucleus is infinitely large. So Coulombian force will be initially zero. But you know, as the alpha particle will move towards the target nucleus, then R will decrease, that is distance between the alpha particle and the nucleus will decrease, and the Coulombian repulsion will be experienced by the alpha particle. So the Coulombian force exerted by the nucleus on the alpha particle will deviate its path. So initially the alpha particle follows a straight line path, but after some time it will get deviated from its original path. Okay. So I have shown this by this curve. You can see that the alpha particle gets deflected, and see in the figure this point A. This is the point which is closest to the nucleus. During the whole motion of alpha particle, this alpha particle is closest to the nucleus when it is at point A. Okay. And so after this point A, now the alpha particle moves along this direction Y. Okay. It gets deflected and moves towards Y. And again, as the separation between the nucleus and the alpha particle increases, the force of repulsion will decrease, because you know Coulombian repulsion is inversely proportional to R square. And when this R will tend towards infinity, this force again will tend to zero. It means there will be no Coulombian force experienced by the alpha particle when it will be infinitely separated from the nucleus. And that's why again the alpha particle will follow a straight line path. And I have shown that a straight line path by this line OY. This OY is actually a asymptote, and this represents the final direction of motion of the alpha particle. Okay. Now, if you proceed the initial direction of motion of the alpha particle, let us say that alpha particle was projected initially with velocity v0, and if you proceed the direction of this v0 and draw a perpendicular from the nucleus, which is actually center of force or center of scattering, you can say, then the distance or the length of the perpendicular drawn from the nucleus to this initial direction of motion of the alpha particle is nq, which I have marked here. This is equal to p. You know, this p is called impact parameter. This is called impact parameter. This is the least distance or the perpendicular distance of the initial direction of motion of our projectile from the center of force or from the center of scattering. Okay, so this P is what? P is impact parameter. Okay, and as you can see, this XO represents the initial direction of motion of our projectile. Okay, and this OY represents its final direction of motion. And you know, the angle between the initial direction of motion of the projectile and its final direction of motion, that is called angle of scattering. So in this figure you can see that this angle phi which I have marked here, this is actually the angle of scattering. So phi is what? This is a scattering angle, or you can say angle of scattering, a scattering angle. Okay, a scattering angle. And for calculation, I have assumed that this angle XOA, angle XOA is equal to theta naught. I have assumed. But you know that this path XAY, this path is symmetrical about the axis of symmetry which passes through this point A. And that's why, since this trajectory or this path followed by the alpha particle is symmetrical about its axis of symmetry, so this angle YOA will be also equal to theta naught. YOA, this will be also equal to theta naught. Now see the geometry of this figure. If you want to relate the angle of a scattering phi to this angle theta naught, you can see that actually what will be this phi? Phi will be simply equal to pi minus 2 theta naught. See the figure. Because this whole angle will be equal to pi, and when you will subtract this 2 theta naught from pi, you will get phi. So phi angle of a scattering is related to this theta naught by this relation. Phi is equal to pi minus 2 theta naught. Okay. Actually, what I have just explained to you on the basis of this figure, each and every thing I have mentioned here in language for your convenience. You can note down these things, because when there are so many complaints of the viewer that when we see a video we learn everything, but when we want to write those things, something will be missing. So for a good note, for your examination purpose, I have written all these facts here, and I am just giving a reading for your convenience, and that will prove that what I have actually explained I have already mentioned here. So you can see I have written here, let the incident alpha particle is projected from infinity along the direction XO. Okay, this particle will follow an unbound orbit, as I have told you, because the force is a repulsive force, so the path will be unbounded path or unbound orbit. Because being initially at an infinite distance from the center of force, will start journey along a straight path XO. As it approaches the center of force, it begins to deflect from the straight line path, and after some time approaches the point A, the point closest approach to the center of force. All these things I have just explained. Okay, and thereafter the particle begins to move away from the center of force and finally picks up the straight line path OY. Okay, phi is the angle of scattering. Okay, and the particle's trajectory is symmetrical about the axis of symmetry OA, and so you can say that angle XOA is equal to YOA, and this is equal to theta naught, as we have assumed. And Just I have explained that this phi will be equal to pi minus 2 theta naught, and so you can write from here that this theta naught will be equal to this much. This is pi by 2 minus pi by 2. Okay. Now we will see two things. First of all, we will prove that the trajectory of the particle will be a hyperbola. Although you have already studied in my previous videos that if the central force is repulsive, definitely in that condition total energy of the system will be positive, and when total energy will be positive, eccentricity of the orbit will be greater than 1 and the path will be what? Path will be actually equal to path will be actually a hyperbola. So the same situation is here. So we will see first of all that the trajectory followed by the alpha particle will be a hyperbola. But how? I have again proved it here. Okay. Now you can see we have considered that initially the particle alpha particle has been projected with velocity v naught, and at the initial position the alpha particle is far apart from the nucleus. It means there will be no Coulombian interaction between the alpha particle and the nucleus when it was at its initial position. Okay. So if you consider that the total energy of alpha particle is E, then you know total energy will be the sum of its kinetic and its potential energy. Okay. But as here potential energy means electrostatic potential energy, and you know if there are two charges, let us say Q1 and Q2 of same sign, both are positive and they are separated by a distance r, then what is the electrostatic potential energy? You know this is equal to 1 over 4 pi epsilon naught Q1 times Q2 divided by r. This is the expression for Coulombian potential energy when the force is repulsive. Okay, potential energy positive. But as you have considered that at the initial, when the alpha particle is at its initial position, this r is equal to infinity. So here I have written, here you can see in our present problem, one of the charge is charge of the nucleus, which will be Ze, where Z is the atomic number or number of protons, and 2e is the charge of alpha particle. Okay. But at initial moment r is infinity. So when you will put r equal to infinity, this energy will vanish, this will be zero. So you can say that at initially the potential energy, that is electrostatic potential energy of the alpha particle is zero. Actually, you know, potential energy means energy of interaction. But when the alpha particle was just projected, at that moment alpha particle was not interacted with the nucleus. So there was no interaction, and so potential energy will be simply zero. You can give this argument. And that's why we simply say that at the initial moment, the total energy E of the alpha particle is equal to simply its kinetic energy. So kinetic energy at initial moment represents the total energy of alpha particle. And as you know, in this process, nucleus will be never in motion. So nucleus will have no kinetic energy. So total energy of this colliding system, E, will be simply equal to the total kinetic energy of the alpha particle in the beginning. Okay. So, and you have assumed that its initial velocity is v naught. So E will be equal to half m v naught square. Okay. And from here you can see that you can write mv naught whole square will be equal to 2me, and therefore mv naught will be equal to a square root of 2me. Okay. Now you know how angular momentum of this particle will be defined. You know angular momentum is simply the moment of momentum. It means moment of linear momentum is called angular momentum. So if you want to find the magnitude of the angular momentum of this alpha particle, you should multiply the initial momentum of the alpha particle with this perpendicular distance. This perpendicular distance is called moment arm. And you know, in a central force field, angular momentum never changes. So alpha part, whenever you will find the angular momentum of alpha particle, that will remain same, because during the motion of a central force field, angular momentum of the particle remains conserved. So if you find the initial angular momentum of the alpha particle, that will be the angular momentum of alpha particle at any moment. Okay, that will be at any moment. So you can simply say that this is angular momentum, not initial angular momentum, because angular momentum never changes. And this angular momentum J will be equal to moment of momentum. So this will be mv naught at times p. P is here impact parameter, which acts just like moment arm. Okay. But you have find that mv naught is equal to a square root of 2mv. So let us put it here, and therefore J will be equal to P times a square root of 2mv. Okay. This is angular momentum of the particle, that is the alpha particle. Okay. Now, as I have told you earlier that in my previous video we have discussed the trajectory of a particle moving in a central force field. The general result for the trajectory of a particle moving in a central force field, when the particle actually obeys the inverse square law, then you have seen this trajectory is given like this. This is 1 over r equal to mc by j square times 1 plus epsilon cos theta. Here m is mass of the particle, c is a constant. In case of Coulombian repulsion, this c will be equal to 1 over 4 pi epsilon naught q1 times q2. q1 times q2. This is c in case of Coulombian repulsion. And in case of Coulombian attraction, you have to put here minus sign. But in the present situation, since we are considering Coulombian repulsion, not attraction, so C will be this. Here Q1 means charge of nucleus and Q2 means charge of alpha particle. Okay. And this epsilon, you know, this epsilon is called eccentricity of the orbit or eccentricity of the path. And you have learned earlier that this eccentricity of the orbit is given by this relation, epsilon square equal to 1 plus 2 ej square by mc square. I have written this relation directly here because I have already provided video on this previously. So I have guided you. You must watch the previous video on central force field. Okay. Now, let us put this value of epsilon in this expression, and you can see then after substituting the value of eccentricity epsilon, 1 over r will be equal to mc by j square times 1 plus a square root of 1 plus 2 ej square by mc square times cos theta. Okay. And when we have discussed the energy of a particle moving in a central force field, then you have seen if the central force field is a repulsive central force, then the total energy is given like this. This is half mr dot square plus j square by 2mr square plus c bar. Actually, the sum of the first two terms represents the kinetic energy of the particle. And this third term C by R, this represents the potential energy. Here in present situation, C, as I have told you earlier, this will be equal to 1 over 4 pi epsilon naught Q1 Q2, and here Q1 times Q2 means 2 ZE square. Okay. And this is positive, you can see. So you can see this relation. In RHS of this relation, each and every term is positive. First two terms represent the total kinetic energy, and kinetic energy always positive. Since C is positive, so this last term, that is potential energy, is also positive in this case. So you can say that the total energy in present situation will be positive. This is a general fact. Whenever motion takes place in a repulsive central force field, then the total energy is positive. And if E is positive, you can see the expression for eccentricity. This is 1 plus a square root of 1 plus 2 Ej square by mc square. Since this 2 Ej square by mc square is positive as E is positive, so the number inside the square root is greater than 1. So its square root will be greater than 1. And you can say that eccentricity of the orbit of this alpha particle in the present context is greater than 1. And you know from coordinate geometry that if eccentricity of an orbit is greater than 1, the orbit will be what? That will be simply a hyperbola. So now it is clearly proved that the alpha particle will follow a hyperbolic path during this interaction. So in Rutherford alpha scattering experiment, the orbit or the path followed by the alpha particle is what? That is a hyperbola. This is a very important fact, and such problem is asked in objective questions. In your examination, you will see that there will be a question that the path followed by alpha particle during Rutherford alpha scattering experiment was a hyperbola, was a parabola, was an ellipse, was a circle. What will be the answer? Answer will be hyperbola. Why hyperbola? Because the eccentricity is greater than 1. Okay? I think we have a clear-cut picture now of this fact now in your mind. Okay? Now, as you have seen that in this, see this figure, when our alpha particle is at point x, that is, it is at an infinite separation from the nucleus, then the angle theta, which you have mentioned in the equation of trajectory, that was actually equal to theta naught. So you can say when r is equal to infinity, then theta is equal to theta naught, not theta. Okay. So now let us put r equal to infinity and theta equal to theta naught in this equation 2. Since r is infinity, so 1 by r will be what? This will be 1 by infinity, and that will be equal to 0. And in RHS, at the place of theta, then we will write theta naught. So now this equation 2 will become what? You can see this becomes 0 equal to mc over j square times 1 plus a square root of 1 plus 2 ej square mc square times cos theta naught. Okay? And so you can write this bracketed term will be 0 because mc by j square is not 0. So this can be written as 1 plus a square root of 1 plus 2 ej square over mc square times cos theta naught is 0. And when you will bring this 1 in RHS, this will be 1 a square root of 1 plus 2 ej square by mc square times cos theta naught, that will be equal to 0. I have underlined it. Don't think that your cos theta naught is under a square root. It is not under a square root. Okay? Now see. Now let us square this equation both sides. After squaring, this square root will removed, and cos theta naught will now become cos square theta naught, and in RHS you will get 1. Okay? And so you can say that this 1 plus 2 ej square over mc square will be equal to 1 over cos square theta naught. And 1 over cos square theta naught, you know this is sec square theta naught. Okay? And now again bring this 1 in RHS. and that in RHS then there will be sec square theta naught minus 1, and you know this is equal to tan square theta naught. So I have written here that this 2ej square by mc square equal to tan square theta naught. Now we will put the value of j which we have obtained here. See, j is equal to this much. This is p times root over 2me. So now put at the place of j square p square into 2me. I have mentioned it here. You can see j is equal to this much, and this will be used in that equation, and your result will be 2e over mc square times p square times 2me, and that is equal to tan square theta naught. Okay, and you can see this m and this m will cancel out, and tan theta naught, that will be a square root of this much, and after taking the square root, your result will be 2pe over c. Okay, but you have learnt earlier that this theta naught is equal to what? This is pi by 2 minus pi by 2. Okay, so you can write tan pi by 2 minus pi by 2 is equal to 2pe by c. But from trigonometry, you know tan pi by 2 minus pi by 2 is equal to cot pi by 2. So you can write cot pi by 2 is equal to 2pe over c. And therefore, if your aim is to find the expression for the impact parameter p, that will be c over 2e times cot phi by 2. I have written this equation as an important equation because in the next video, when we will learn about the scattering cross section, we will need this expression. So I have marked here a different equation number a1. Okay, and if your aim is to find the angle of a scattering and you know the impact parameter, you can see this relation. Cot phi by 2 is this much, but you know cot phi by 2 is equal to 1 over tan phi by 2. So tan phi by 2 will be simply equal to reciprocal of this. So tan phi by 2 is c over 2p. But what is this c? We have seen earlier, in this case, in present case, c is equal to 1 over 4 pi epsilon naught 2ze square. This is c. And 2 e, not only e, but 2ep. Okay. So this equation is the expression for the angle of a scattering, and you can see this angle of a scattering is related to the impact parameter p in this way. And as I have told you earlier that in this video our aim was only to find the angle of a scattering in terms of the impact parameter, or to obtain the relation between the angle of a scattering and the impact parameter. But the most important fact, most important problem of this scattering is to find the differential scattering cross section and total scattering cross section, and that will be dealt in the forthcoming video. So definitely after watching this video, you must continue to watch the next video on this Rutherford scattering, because after these two videos the solution of this problem will be completed. Okay, thank you very much.